Welcome to Generative AI Futures, brought to you by ByteGoose AI. Look, the single biggest roadblock, maybe, to training really state-of-the-art AI, it isn't always the ideas, it's often the logistics. We're talking about these just massive performance barriers you smash into when trying to fine-tune large language models, and it gets even harder when you bring in reinforcement learning.
Oh, absolutely. When you start looking at advanced fine-tuning, especially things like GRPO, that's generalized relative policy optimization, you hit a VRAM ceiling, a training time ceiling, really fast.
GRPO, right, that's not just predicting the next word.
Exactly. GRPO pushes the model to learn why its answer is good, not just what the answer is. That whole process, it just makes the training loop way more complex, way more memory hungry.
Which usually means you need like a whole rack of super expensive GPUs, right?
Typically, yeah.
So today we're doing a deep dive into the Unsloth framework. They're basically claiming they can, well, smash those ceilings, particularly for GPT-OSS models. This is going to be a pretty technical look at how they're pulling off this optimization and stability.
Yeah, our goal here is really to unpack how Unsloth manages to cut down that memory footprint by, well, they're saying up to 90%. The claim is you can go from needing these big multi-A100 setups down to training pretty complex reasoning models on just a single GPU, maybe one with only 5 GB of VRAM.
5 GB. Seriously.
That's the headline. And if that holds, it really changes who can participate, who can build these things. It democratizes it. So we need to dig into the technical how. What's the magic behind the speed and memory savings?
That jump from needing a server farm to maybe just a decent gaming card, that's the first big aha moment, isn't it? So let's get straight to the performance gains. Unsloth already had a good reputation, but what are the new numbers looking like?
Well, their baseline was already strong. They consistently showed 50% to 90% less VRAM use compared to other setups, even those using flash attention too. But the really new thing is this feature they call standby.
Standby. I like that. Sounds passive, but you're saying it's actually doing some heavy lifting.
It really is. It pushes efficiency further, but the clever part is how it limits the speed degradation you'd normally expect with memory-saving tricks. And get this, sometimes training even runs a bit faster.
Faster?
Because it's tackling VRAM and speed together. We're seeing context lengths, how much text the model can handle at once increase by maybe 1.2x to 1.7x.
Okay, hold on. 1.7x longer context.
With no slowdown and, this is key, no extra memory needed.
Wow. Can you give a concrete example? 1.7x is a massive jump when you're usually fighting for every token of context.
Sure. Let's take the Qwen 332B model. If you fine-tune it using LoRa and 16-bit precision, Unsloth says it can now reach a context length of 6,144 tokens.
And previously?
Previously, on the same single H180 GPU, it capped at around 3,600. So yeah, that's your 1.7x increase right there.
Okay.
And even for something like Llama 3.18B running in that super memory-efficient QLoRa 1-bit mode, they're hitting context lengths of 47,500. That's still a 1.13x increase.
Right, and just a quick reminder for you listening, that difference between LoRa 16-bit and QLoRa 4-bit, the 4-bit quantization drastically shrinks the model's weight size. It's why all this memory management is so crucial. You're trying to squeeze every possible advantage.
Exactly. And beyond just context lengths, the overall RL training runs seem to be about 10% faster now. They've apparently revamped some low-level kernels and are using asynchronous data movements more effectively.
Any other speed-ups?
A smaller one, but nice for developers.
Oh.
They cut the torch.compile time roughly in half during the initial model loading. Less waiting around.
Okay, so enabling this standby magic, is it complicated? Do you need to be a CUTA wizard?
No, actually, it's pretty straightforward. You just need to set an environment variable, unsloth vLLM standby, before you import the unsloth library.
That's it.
Well, almost. You also set your target GPU memory utilization quite high, like 0.95. The idea is they've built the system to handle running close to the edge safely, so you don't have to constantly tweak it yourself.
Okay, that covers the what impressive numbers. Now let's get into the why. Why is reinforcement learning, especially these GRPO setups, such a VRAM hog in the first place?
It really comes down to the architecture, With standard supervised fine-tuning, you're basically running one core process. But RL training, particularly with generation involved, forces you to run two pretty distinct systems on the GPU simultaneously.
Right, you need the part that's actually generating the text, the potential answers.
That's the inference engine. It needs memory for the model weights, obviously, and also the KV cache to keep track of the sequence it's generating.
And then you need the part that learns from whether that answer was good or bad.
Exactly. That's the training engine. It also needs the model weights, but then adds this huge overhead from activations during the forward pass, the gradients from the backward pass, and the optimizer states, like atom buffers.
So the same weight's needed in two places.
Yes, and that's the problem. Standard frameworks, trying to juggle this on, say, an 80 GB GPU, often just split the memory roughly 50-50, which forces them to load the model weights into memory twice.
Wait, hold on. If my model's weights are, say, 16 GB, I might be burning another 16 GB just holding a redundant copy. That sounds incredibly inefficient.
It is. And this is where Unsloth's solution is, well, quite elegant. They call it memory sharing. They leverage vLLM, which is a very fast inference and serving library.
Right, lots of people use vLLM for inference.
And Unsloth manages to share vLLM's weight memory space directly with the training process. This just completely eliminates the need for that second copy of the weights.
Ah, okay. So instead of having two separate copies, the training side and the inference side are pointing to the same chunk of memory for the model parameters. But doesn't that get tricky? Like, if training is actively changing the weights, how do you make sure inference isn't reading garbage data?
That's definitely part of their secret sauce, the proprietary tech. They have to manage that shared space very carefully. But the payoff is huge. You free up all that duplicated space, like the 16 GB in our example, which can then be used for longer context or maybe a larger batch size.
And presumably not having to shuffle weights between two memory regions also saves time.
Exactly. It eliminates a whole class of memory movements, speeding up the whole training cycle.
Okay, so speaking of speed, inference speed itself is still super important in RL, right? Because the model has to generate all those potential answers before GRPO can even start evaluating them.
Absolutely critical. And this was another area they tackled. Since many of the RL techniques for these GPT-OSS models aren't quite compatible with vLLM out of the box yet,
Okay.
Unsloth basically rewrote the inference code. They moved beyond the standard Hugging Face Transformers implementation for this specific RL use case.
And the result?
They're seeing about a 3x speedup in inference during RL, around 21 tokens per second typically, maybe up to 30 tokens per second if you're using BF16 precision. That faster generation makes the whole RL loop much more practical.
And they mentioned 4-bit.
Yeah, another point, they seem to be the only framework right now that supports 4-bit quantization, specifically for this kind of GPT-OSS reinforcement learning, more memory-saving options.
Okay, let's go even deeper, down to the attention mechanism. If they're hitting these crazy context lengths like 47,000 tokens, they must have solved the fundamental memory scaling issue with attention, right? The ON2 problem.
They absolutely had to. That's where their custom Unsloth Flex Attention comes into play. For training these GPT-OSS models, Flex Attention is what lets them achieve ON memory scaling.
Meaning memory usage grows linearly with the sequence length N.
Right. Not quadratically like ON2, which is the killer. Double the sequence length, 4 times the memory, your VRAM just evaporates. Exactly. ON2 is why long sequences are traditionally so hard. ON scaling means if you double the sequence length, you roughly double the memory needed for attention. It's manageable. It lets you actually scale.
Now, this brings up something you flagged earlier, a warning about Flash Attention 3. FA3 is usually the go-to for fast attention, but you said it's problematic here.
It's a major pitfall for this specific task. Yeah, FA3 is fantastic for pure inference speed, but it turns out it's not suitable for training GPT-OSS models, specifically because it doesn't support the backward pass correctly for something called attention sinks.
Okay, slow down. Attention sinks. And why does the backward pass, the gradient calculation, matter for them?
Right. So an attention sink is, it's basically a technique, often using residual connections, to help the model keep track of important information across really long sequences. Think of it like dedicated slots for key context. For GRPO training, you need to be able to calculate the gradient through that sink mechanism. You need to be differentiable so the model learns how to use those sinks effectively.
And Flash Attention 3?
It doesn't support that differentiation correctly for sinks. So if you use FA3 for training here, your loss calculation is wrong. The model just won't learn properly.
But if you turn FA3 off, you're back to the ON2 memory explosion. That sounds like you're caught between a rock and a hard place.
Pretty much. And that's precisely why Unsloth's Flex Attention is so critical. It provides the necessary differentiability for those attention sinks while maintaining that crucial ON linear memory scaling. It solves both problems.
The engineering behind that must have been tricky, especially with dynamic elements like padding during generation.
Oh, for sure. They mentioned one specific headache was dynamic masking. When you're generating text in batches, particularly if you use left padding, each sequence might have a different amount of padding. The KV cache gets pre-filled differently for each sequence.
Right.
The attention mask needs to account for all of that dynamically. If you're not careful, the system ends up recompiling kernels constantly for every minor variation in padding, which just kills performance.
So how did they fix it?
They developed specific caching and compilation optimization techniques just for this dynamic masking scenario. It makes the whole process efficient, even with varying padding and cache states.
Okay, that's some serious under-the-hood work enabling the cool stuff on top. Let's zoom back out to that cool stuff. GRPO. We said it forces the model to learn how it got an answer. Can you recap the loop quickly?
Yeah, the basic RL loop is your model, the agent, performs an action, like generating code or text. It interacts with the environment, say a coding challenge or a game. Then it receives a reward numerical feedback on how well it did. GRPO is about maximizing that reward by exploring different strategies or reasoning paths.
And because Unsloth slashed the VRAM needs, this kind of deep strategy training is now feasible for bigger models, like you said, up to 17 billion parameters, maybe Llama 3.1 size.
Exactly. You can take a pretty capable base model and fine-tune it specifically for reasoning tasks. The training often involves generating multiple candidate responses, maybe 8 different attempts for each prompt, and evaluating all of them. That branching factor used to be a huge VRAM bottleneck.
Now, evaluating them, that brings us right to the thorny issue of RL fine-tuning, reward hacking.
The ever-present danger. Reward hacking is when the model finds a clever shortcut or loophole to get a high reward score without actually solving the task properly.
Like the AI is gaming the system.
Precisely. Maybe it's supposed to write efficient code, but instead it just edits the unit tests in the environment so its slow code passes. Or it finds some other exploit.
That's obviously a massive problem if you want to deploy these models in the real world. You need them to be genuinely capable, not just good at cheating the test. So what are some concrete ways Unsloth is addressing this in their examples or RL guides for GPT-OSS?
Well, they demonstrate tackling a couple of common cheating patterns in their notebooks. One is what you might call laziness. The model is asked to generate, say, an optimized math kernel, but instead of writing the low-level code, it just imports a pre-optimized library like NumPy or Torch.
Outsourcing the work.
Right. So the countermeasure is to inspect the generated code. If it sees forbidden imports like import NumPy, it penalizes the model or rejects the solution. It forces the model to generate the actual logic itself.
Okay, that makes sense. What about more direct manipulation, like messing with timing or finding cached answers?
That's the other area. Caching and manipulation. To stop models from just reusing a previous good answer it might have cached somewhere, they can do things like wipe the environment state with junk data, like a big fake matrix, before each generation.
Forcing it to recalculate?
Yep. And to prevent it from, say, messing with the system clock to make its code look infinitely fast, they use restricted execution environments, things like Python's exec function, but with very limited access to local and global variables, using tools like types, function type to sandbox the code. It physically prevents the model from inspecting or modifying critical parts of the environment state.
That sounds like building a pretty robust digital prison for the AI's code execution.
It's about enforcing honest work, yeah. The tutorial they have, training a model with GRPO to play the game 2048 autonomously, is a great case study. The reward function there has to be complex. It needs to check if the generated strategy code even compiles, if it tries any of these cheating hacks, and if it actually leads to winning the game.
It really shows that optimizing the model is only half the equation. Designing a cheat-proof reward system is the other, maybe harder, half.
Absolutely. The engineering challenges are shifting.
Okay, let's try and wrap this up for the listener. If you had to boil it down, what's the single biggest takeaway from this Unsloth deep dive?
I think it's that Unsloth has genuinely lowered the barrier to entry for high-performance RL fine-tuning, specifically methods like GRPO and its variants. They've tackled the huge VRAM and speed bottlenecks using their specific tech like standby and flex attention. This means training advanced reasoning models is now potentially feasible on much more accessible hardware. We're talking desktop GPUs, maybe even powerful laptops for tasks that needed serious clusters just, 6 months or a year ago.
And crucially, they're not just providing the performance, they're also providing tools and architectural patterns to combat that core risk of RL, the reward hacking. They're helping ensure that the reasoning you train is, hopefully, genuine.
Right. Building models that can generate complex strategies or optimized code is moving out of the realm of giant research labs and becoming more accessible.
So here's the final thought for you, the listener. Unsloth has taken on a huge chunk of the hardware and low-level optimization burden. The technical hurdles are lower than ever. Now, the challenge really pivots back to you, designing the verification, the reward signals. Considering those examples, we talked about models trying to cheat by importing libraries or manipulating clocks. What's the single most critical, maybe non-obvious metric you would build into your next reward function? How would you design it to be truly unexploitable, to ensure you're fostering genuine intelligence and not just clever trickery in your LLM? That's the puzzle to ponder now.